Thanks so much, Aisha, and thanks to everyone who invited me here. I'm really happy to be here, and it's a privilege to be able to talk to you all, and I'm looking forward to hearing your thoughts at the end about this topic as well. So I'm going to speak today about algorithmic monoculture and the ethics of systemic exclusion. So as Aisha mentioned, I am lucky enough to be a computationally inclined philosopher who gets to exist in both computer science and philosophy world, and I couldn't do that without my fantastic co-authors. So you see them here in their full glory, but their little heads will pop up on the slides as I draw on projects that I've done with them. So look forward to my majestic co-authors returning, and thank you to all of them for the joyful work that we've been able to do together. So imagine you are a hiring manager, and out of hundreds or thousands of resumes, you have to find 3 people to interview and 1 to hire. And this, in our computer science terms, is a very information-constrained problem. We have time constraints. We have information constraints. There are some things that we might want to know and we're not allowed to know, perhaps for good reason. There are privacy constraints. And perhaps most importantly, the feature space is really undefined. We don't actually know what makes a good employee right now or what will make a good employee in the uncertain future. And so into this morass of uncertainty step automated hiring systems. Most systems will do this first round screening, so discard about half of applications before a human being ever looks at them. And 98% of Fortune 5 companies use some version of an applicant tracking system which has some kind of sorting, but many of them use this more extensive first round screening algorithmic system as well. And the hope is that these hiring systems will save time and money, reduce bias, perhaps choose better candidates, and most importantly, produce more consistent judgments. And it's that consistency that I want to focus on in the talk today. So imagine from the candidate perspective, you're applying to what I hope are 3 MIT area grocery stores: the Target, the Daily Table, and the H Mart. I'm getting some of this, so I'm hearing these are not the best grocery stores in the area, but maybe you didn't know that. Maybe there are yet better grocery stores that you should have applied to. I am going to defend the H Mart, however. Okay, so you imagine, perhaps naively, that when you submit these 3 separate applications to 3 completely separate business entities, that your file will be screened by 3 different sets of managers, actors, whoever. Human beings will look at these files. But it might be that all 3 companies have purchased software from an automated resume screening provider like HireVue. And so you are, unbeknownst to you, experiencing algorithmic standardization, where decisions that were previously made by many different people are now made by one screening company. And so we can say that whatever else they do, automated decision-making systems have the potential to standardize by enforcing the same classification on the same token applicant file every time it's encountered at scale. And then we might ask, is this standardization a problem? In a context where the largest algorithmic screening providers have clients that include 60% of the Fortune 100 and 8 of the 10 largest federal agencies, is it a problem if the same applicants re-encounter the same systems over and over? And the reason I think this is an interesting AI and society problem, an interesting ethics problem, is that standardization at scale is one of the features of automated but not human decision-making. If you've ever worked with a bureaucracy, you know that it's actually very hard to get humans to make the same decisions, even on the same cases. If you show people whose whole job it is to make decisions, like doctors, lawyers, judges, the same file 3 months later with names and other details removed, they'll make a different decision about 25 to 30% of the time. So even the same individual will sometimes make a different decision on the same case over time. And that's not even counting the diversity of between decision maker choices. So this is a case where algorithmic decision-making and human decision-making regimes might have importantly different features. rather than cases that we often talk about, which are also important, in which it's just that algorithmic decision-making perhaps exacerbates patterns that are already present in the other decision-making regime. So in the talk today, I want to go through what is it that standardizes algorithmic decisions, when should we consider standardized decisions to be of moral concern, and when they're of moral concern, what is it that we should do? So in this room, I don't need to go through one source of standardization, which is, of course, just the basic nature of a deterministic algorithm. Put in the same inputs, you get the same outputs. But I want to talk about a more subtle source of algorithmic standardization, which is algorithmic monoculture. So monoculture is a metaphor drawn from agricultural science. We have the case of industrial farming, where previously you might have had gardens that were intercropped with many different plants. Each of those plants drew different things from the soil, used different nutrients, put different fixed nutrients back in the soil, etc. Then when we move to industrialized agriculture, it becomes more efficient to take a tractor and run it down the same line of plants and harvest the same plants at the same time. But we know that if we plant the same field with the same crops over and over, eventually we get nutrient collapse. So metaphorically, we might think of this as an algorithmic monoculture. As Manish and co-author John Kleinberg have said, algorithmic monoculture is a state in which many decision makers all rely on the same algorithm. And in this lovely 2021 paper, they point out that this can have medium-term collapse effects, where even though initially it might be better for the decision makers themselves, it might end up in the medium term causing them problems by their own lights. So what are some other sources of algorithmic monoculture? So the first, of course, is we literally use the same model in one domain. And we're going to call this mechanical algorithmic monoculture. So necessarily you have to get the same outcome. And this is not as unusual as you might think, given roll-ups and mergers by various private equity firms that are trying to create one actor in an entire domain. But since this isn't a political economy talk, we will move on to think instead about a relaxed definition of algorithmic monoculture. So if Kleinberg and Raghavan's definition is this pure algorithmic monoculture where all decision makers rely on the same algorithm, it might not be that realistic in all of our decision settings. So when HireVue builds an applicant screening algorithms for grocery stores, it's not actually going to give the same algorithm to all the grocery stores. Sufficiently big actors desire customization. It has to be tailored to them. So instead of this case, we're going to have a relaxed monoculture where, these houses sure look very similar, but if you look closely, they have different doors, they have different windows, they have different awnings. They're not exactly the same. And in a similar way, we're going to define algorithmic monoculture as the state in which many decision makers rely on similar algorithms in a way that I'll specify in a moment. So here we might be thinking of the same provider is still building algorithms, but they're slightly different for each of the grocery stores. Or even there's a different provider who's providing algorithms to a third grocery store. So in that case, why might we think that decision-making outcomes would still be correlated? So one reason is that machine learning is built on a wonderful tradition of component sharing. So we work really hard to get good data sets, and then it would be rational for many people in the same decision-making ecosystem who want to do the same task to rely on the same data set. So for a long time, ImageNet was the largest labeled data set of images in town. So it made sense that a lot of computer vision papers would all use ImageNet. Likewise, for a certain time period when BERT was the best model for certain language tasks, a lot of papers at the same conference would all rely on BERT. We might also have libraries that are best in class at a moment at a time, and evaluations. Academics are competitive people. At least, I hope that's not too controversial to say. So if someone puts out a big shiny benchmark, a lot of people are going to try to meet that benchmark if it gains social prestige. And so attempts to meet the same benchmark might also homogenize the outputs because we're aiming towards the same goal. So we have these standardizing forces that are built on the tradition of sharing in machine learning. And anecdotally, we've seen that previous data curation efforts like ImageNet have standardized training corpora, and in doing so, standardized errors, such as reliance on the same spurious cues or shortcuts like background textures to predict foreground objects. So here we have an image of a fox squirrel on the left, but ImageNet models are very likely to say that it's a sea lion. On the right, we have a focal image of a dragonfly, but ImageNet models are very likely to say it's a manhole cover. So why is that? Take a minute, look at the pictures. Okay, great. So we think it's because of these strong background textures. The background texture of the wet rock is similar to a sea lion. The cross-hatching of, I assume, the lawn chair is similar to a manhole cover. And so what's important here is not that models make mistakes. Of course they make mistakes. It's that training on the data set means they make the same particular mistake. There can also be standardization due to use of shared data in regimes where there's only one data set. So Common Crawl is an attempt to compile and clean the data from the entire internet. But unfortunately, there's only one entire internet. So even if we had a competitor to Common Crawl, it would be attempting to get all the same data from the same source. Likewise, we might have very large models that are trained with significant computational resources, often across multiple modalities. And I don't know about you, but if I built a $10 million model, which I have not, I wouldn't want to just immediately throw it in the trash after I used it once. I would probably try to use it for as many different things as I possibly could. So the concern here is that adapting the same model for many different tasks could lead to a single point of failure. And in some co-authored work, a paper called Ecosystems Graphs, we've tried to show this by looking at dependencies in the foundation model ecosystem and showing that there are significant hubs where a whole bunch of different models from different companies will train on the same data set, like the pile, or different APIs across many different companies will rely on the same underlying base model. All right, wonderful. So I've suggested that there are many reasons why algorithmic decisions might be standardized. But why do we care about this in this context? It's because we think that algorithmic monoculture has the potential to homogenize outcomes. So what does this look like? So imagine people are interacting with some kind of deployed machine learning system. So there are multiple people, and they're interacting with multiple decision makers. This is different from the context that we often look at in, let's say, algorithmic fairness, where we're imagining a regime of one decision maker and a population that has a bunch of subpopulations. Now we're thinking about what's the cumulative effect of multiple decision makers on a population. So we're switching the frame a little bit. So now we want to say, what is the cumulative pattern of the outcomes that they receive? And we can either think about these just in terms of their positive or negative aspects. Did they get, let's say, the good or not? Or we can think about these in terms of their errors. Was the correct judgment made on them? And is there a pattern of systemic failure or systemic error? So we're going to call outcome homogenization when an individual or a subgroup receives the same outcomes from decision makers. And those could be positive or negative. Then we're going to say an individual experiences systemic failure if every decision-making system fails for that person. And in classification settings, that's going to mean they experience a systemic failure or error if every decision-making system misclassifies that person. So how do we measure this? We can't just count, right? Because if we count, we would over-index on the fact that the systems do make some errors, and those errors would naturally collide even if the systems were completely independent of each other. So we just minimally need to normalize for that error rate. So we need to say, compared to what we would have expected if these systems had been totally independent, how much more homogeneous are the outcomes than that? So you can imagine if each of the systems is very bad, it makes 40% errors, there's going to be a high sort of baseline error rate, but we still might want to know, are they more homogeneous than that? Now, this doesn't mean, by calling it a baseline, doesn't mean that we're committed to saying that independence is actually the right answer. In fact, we suspect in a lot of cases, the sort of right degree of correlation would be somewhere in the middle. But in a lot of regimes, we may not know what is the correct degree of correlation. So we're just viewing this as a baseline where we're saying empirically, how much more correlated are they than this baseline? Okay, so in a study of this, we looked at the HAPPY data set, and we looked at predictions from deployed APIs in 3 modalities: image, text, and speech. We had 11 classification data sets, roughly 4 per modality, and 3 APIs per modality, so 3 predictions for every data point. And luckily, we also had this over time, from 2020 to 2022. So what we wanted to find out is how often were model errors correlated? And it turned out much more than if the model errors were independent, which is what we would sort of expect. So the observed is the dark blue. You can see on the 0, so all models get it wrong. There are a lot more all models get it wrong than we would have expected based on independence. Now, sometimes when I present this to computer scientists, they say, aha, that's right. That's because those examples are hard. And I say, oh, great, okay, what does it mean to be hard? And they say, well, hardness means that all the models get it wrong. And I say, wait a second, that's what I'm showing you. But is there a model-independent property of hardness? Because if you and I looked at these samples, they wouldn't be hard for us. So I think what we're agreeing on is that there is a model-dependent property of hardness, where these samples are hard for this class of models. But they might not be hard for us, and they might not be hard for some as yet uncreated or perhaps not measured type of model that would be classifying this. And what we notice...
Could I ask one question about that?
Yes.
Were these cases, when they're all wrong, are they all confident they're wrong?
We don't have a confidence measure, but that's a great question. Yeah, thank you. There is a case later where we do have confidence, so thank you. We also notice over time that model improvements don't substantially reduce these failures. So here again we have, out of all the samples that originally the models all got wrong, over the next 2 years, how many of them are improved? And compared to the potential improvements, which is the light blue, many fewer of the models are improved than you would have expected. So the systemic failures tend to persist over time. So in ongoing work that I unfortunately can't share yet, we are trying to audit a real algorithmic hiring vendor and try to figure out how much correlation is in their predictions. But what I want to get to now is the moral question. So if standardizing architectures and data sets improves decision quality, if there's a reason that we have this tradition of component sharing and machine learning, if it improves accuracy, when should we nevertheless think that outcome homogenization is of moral concern? And I think this is a question that I found interesting for some time, because I think the answer is not completely obvious. So this is a challenge. So just to spell it out a little bit more, we often think epistemically, so in our regime of knowledge and what we should know and what we should believe, we often think that each decision maker has a responsibility to act on their best available evidence, all other things being equal. But what if they also have reason to believe, as I think a lot of decision makers should have reason to believe in the machine learning ecosystem, whatever data I have, others also have, whatever learning strategies I consider best, others probably also consider best. Others are likely to combine their data and learning strategies in similar ways and get similar predictive outcomes. And those same predictive outputs might include the same mistakes. And so I should expect that by acting in accordance with the predictions produced by my best data and learning strategy, I might compound errors on the same individuals. And these compounded errors in a high-stakes decision-making regime could systemically exclude individuals from opportunities. So that's the kind of challenge that I want to address in this next section of the talk. And when we think about why it's of moral concern, in the algorithmic fairness space, we often reach first for bias and discrimination. So you could say, maybe this matters because it's a special kind of group-based bias, or maybe it only matters when the individuals who are excluded primarily belong to the same socially salient groups. So a challenge to this has been in my past work and also in other people's past work, what happens if the features that end up being the ones that underlie these correlations are not necessarily standard group-based characteristics. So it could be that there's some kind of consistent decision-making based on arbitrary characteristics. What the sort of joking examples that people use are wearing purple shoelaces or being born on a particular day of the month. But you could also imagine this, I think, more realistically as some difficult to interpret constellation of features that maybe is just hard to find, and we don't know what those features are. So instead of thinking about, for example, biases based on a social characteristic like gender in a large model, so instead of cases like label prediction where you have two possible labels, is this a portrait of an astronaut with the American flag, or is this a photograph of a smiling housewife in an orange jumpsuit with the American flag? You might look at these photos as a human being who has seen a NASA formal portrait before and say, wow, she has the orange NASA suit, she has a giant spaceship, she has a giant space helmet, she has the official NASA badge. Seems like probably an astronaut, but a model might say, no, it's more likely that she is a smiling housewife. But we could also imagine name artifacts that are more individual or particular. So because a lot of large models are trained on data from the internet, that includes forums like Reddit, it turns out that one thing that people like to do on Reddit is talk about politicians they don't like. And it turns out they don't like most politicians. And so regardless of party, if your name is Donald, Bernie, Bill, Hillary, Donald, Mitch, Chuck, Barack, any of these sounding familiar? Or did you get that complete memory wipe that I've been trying to inquire about recently? Okay, so all of these names have negative sentiment associated with them. And you can imagine a certain kind of training task where if you're doing sentiment-based analysis of someone who has one of these names, they get a very slight negative bump. And if they're a 51% candidate, maybe that bumps them down to a 50% or a 49% candidate. So we're not talking about effect sizes probably large enough to move someone from a 99% candidate to a 1% candidate. We're talking about small threshold effect bumps based on sort of arbitrary features like names. And then we might ask this question. If name artifacts have some negative consequences, for example, if they cause a candidate who's already a borderline candidate to consistently drop below a decision threshold, is it wrong to concentrate these kinds of errors on Donalds or Bernies or Bills or Alices or Kevins? Anyone who has those names, come talk to me afterwards. Okay, so in the little flowchart I laid out, we can imagine a couple different responses to this. One is we could say, systemic exclusion shouldn't qualify as bias or discrimination unless it involves membership in some kind of socially salient group. So we could say, hey, I'm just not interested in this Donald-based problem. Call me when we're looking at one of the 7 federally protected categories. And I think it makes sense to say this is not a case of bias or discrimination. And the reason is that if we look at standard definitions of bias and discrimination, it seems like both the scope and the scale of the phenomenon we're particularly talking about is much more extensive. So we're talking about perpetual subordination of specially disadvantaged groups whose political power is severely circumscribed. Doesn't seem like that's happening to Alice's. Discrimination consists of actions, practices, or policies that are based on perceived social group to which they belong, and the groups must be socially salient. So here the idea is whatever your group membership is, whether or not, we don't care whether or not it's sort of metaphysically underlyingly true of you, if it's something that's perpetually attributed to you across a bunch of different spheres of your life, it's structuring your activities in those different spheres. But it doesn't seem like these artifacts are going to swap between spheres, or at least we don't currently have any evidence that we should think they do. There's also this sense of historicity. So maybe an action is compounding a prior injustice, so there has to be some kind of past injustice that it's building on. And this kind of anti-Donald sentiment would only count as discriminatory bias if we had a very permissive definition of bias. Interestingly, some of the original people to talk about bias and discrimination in computer systems, Batje Friedman and Helen Nissenbaum, do have a very permissive definition of this kind. They are thinking about systematic and unfair discrimination, and they say it happens when a system unfairly discriminates if it denies an opportunity or good, or if it assigns any undesirable outcome to an individual or groups of individuals on grounds that are unreasonable or inappropriate. Okay, so that could be anything. It doesn't have to have this history. It doesn't have to be across contexts. So if you think that's plausible, then I think you would think that anti-Donald sentiment is a discriminatory bias. There's also a recent paper that takes this stance, talking specifically about novel algorithmic groups and building on some of our recent work, suggesting that algorithmic groups should be thought of as being discriminated against whenever they're systematically disadvantaged. I don't find this super compelling personally because I think we're losing the characteristic harm of what discrimination is. I think it makes more sense to reserve discrimination for cases that have this, cross-modal, cross-context, time-extended character where it is continuous with socially salient discrimination that structures interactions of human beings. And one way to talk about this is to say, look, if we take one of these overly permissive definitions, maybe, as Kearns and Roth say, we're doing a kind of fairness gerrymandering. So we're picking whoever happens to have gotten left out, and we're saying, well, it was unfair to them. But really, that's kind of post hoc. It's not necessarily the case that we should think of fairness as being about whoever just happens to be in this algorithmic valley. So we have a few different ways of thinking about why systemic exclusion is of moral concern. So I'm going to propose that it's not because it's a type of discriminatory bias. However, if you decide you want to think it is, I think I've given you some resources to structure how you might make that argument. You could say, well, it matters only if bias and systemic exclusion stack in some way. So maybe there's some kind of bias. We already think that's of moral concern in this setting. There's a discriminatory treatment of two different groups. And then we might think, well, it's even worse if the people in the group that are experiencing the lesser inclusion rate, also it's concentrated on individuals within that group and not spread evenly over that group. I think that's possible, but being a philosopher, I'm going to try to argue for what I think is the hardest and the sort of base case example, and then hope that that will flow upwards to these other cases. Because if I can show that it matters for any excluded individuals, but not because they're subject to discriminatory bias, then necessarily it also matters for individuals who are in these more specific cases. Okay, so when is systemic exclusion of individuals because of algorithmic monoculture wrong? Now, there are some philosophers in the room, there are some non-philosophers in the room. One interesting thing about attempts to show that something is wrong is that for most topics, we would expect most moral theories to agree. So if you say, should I kick an innocent puppy just for fun? If your moral theory doesn't end up saying that's probably wrong, we would have this process of reflective equilibrium where we would say, well, something's wrong with the moral theory. That's a problem with the theory. Like the sentiment that that is wrong should be borne out by all moral theories. But systemic exclusion of individuals, I think it's an interesting case where you can see quite a spread of opinions that I'm extrapolating from different theories. So at first I thought, okay, maybe systemic exclusion is wrong because it's unjust. So here we're in the realm of political philosophy. We're thinking about what do we owe to each other. And we might think about this first in terms of democratic equality. So maybe it's fine for individuals, companies, organizations to rank candidates for opportunities by their own metrics. And it's even fine if some people's rankings are kind of arbitrary. But it's when the same hierarchy or ranking is used across the whole sector that it sets the rules of interaction with the domain and monopolizes access to opportunities. And when consistent exclusion of people, because of this, leads to some kind of pernicious social hierarchy, that is when it's unjust. But notice, we have to get to the status of this sad cat. We have to actually create a pernicious social hierarchy. So it has to be the case that the people who are algorithmically excluded are on the bottom of a social hierarchy. And that means this threshold wouldn't support action on most of the empirically demonstrated cases of homogenization. So this is one of the reasons that I think it's really important to try to do kind of a cycle of empirical study and then philosophical theorizing. Because I think this would be a much more compelling talk if I could stand up here and say, there's an algorithmic underclass of people who will never get any opportunity across any domain of life. And so yes, Elizabeth Anderson is correct that it's unjust to them. But I don't think we see that, at least not now. And I would need that to be empirically demonstrated before I said that to you. So what if instead we think about something like Walzer? So we say, hey, there are different domains, spheres of life, different kinds of social good, and we think that these spheres should be separable. So one thing a theory of justice should do is that it should decorrelate social goods. So if you lack a certain social good like healthcare, it shouldn't mean that it's impossible for you to get a loan, and that's one of the roles of the welfare state, is to decorrelate those things. Okay, so interestingly, one of the examples Walzer uses is credit score, which I would think is kind of an abstract gateway to other social goods, not itself a social good. But he uses it, so let's run with that a little bit and say, what if there's this property of being legible to and correctly judged by an algorithm? Shouldn't that be decorrelated from your ability to access employment, welfare, healthcare? Again, I think you have to reach a pretty high threshold where you were genuinely shut out of employment altogether, not just barred from perhaps your preferred employment opportunities. So this is also a really high threshold. So we have a similar worry on a lot of these justice-based theories, that thresholds would not support action on most cases of systemic exclusion due to outcome homogenization. In order to make it work, we would have to move to like an industrial strength egalitarianism. So Rawls, a person that liberal political philosophers often turn to, is not good enough because he says fair equality of opportunity shouldn't be contingent on social class or standing. Well, it would have to be equality of opportunity shouldn't be subject to any morally arbitrary features. But this means, in a lot of cases where we currently think that it would be too cumbersome or burdensome for the state to intervene, the state would have to intervene. So if someone at a local hardware store says, I'm going to interview all the candidates and then I'm going to have a pool of qualified individuals, and then out of those qualified individuals, I'm just going to pick the one who prefers to talk about fishing because they're all qualified and that's going to be my tiebreaker. That would not be acceptable because that's a morally arbitrary feature. So I think not only would this sort of industrial strength egalitarianism require much broader sweeping social revisions, it would also doesn't seem to capture the important features of homogenization due to monoculture, which is that there's something important about the correlation across multiple actors. So instead, I think we should look to theories like contractualism. So here, we're imagining we're all considering adopting some set of rules or decision principles. Which ones should we think are acceptable? Well, Scanlon brings out the big red hammer and he says, a decision-making principle is acceptable if no one affected may reasonably reject it. What is reasonable rejection? Well, it's reasonable when the burden imposed on the rejecter and is substantial, but alternative principles don't impose greater burdens on others. So imagine you're a NIMBY and you say, I don't want this cell tower in my backyard, move it to someone else's backyard, but it would impose an equally great burden on them. We can't just like shift it around the town. There has to be some reason why it's uniquely burdensome to you in order for it to be shifted. But interestingly, the contractualist also has reason to reject a principle on which the same small group is consistently sacrificed for the greater good. And that I think is very analogous to our case here. Instead, we should accept a lottery principle where different randomly selected groups are chosen in different counters, because there we've reduced the error burden, we've spread it over more people, and so the reasonable rejection of the concentrated errors can be substituted for this distributed error model. Interestingly, I think this lottery principle is also shown in the claims framework. So I'll go through this a little more quickly. Well, we could also imagine we're not now thinking about a theory of justice, we're thinking about individual fairness claims. So you have a claim to something when you're owed it for reasons of fairness, and we're gonna say that you have equal claims to the same good, perhaps when you have equivalent properties. So for a kidney, maybe you're the same age and you've been on the waiting list for the same amount of time. Or, morally equivalent, so it doesn't matter whether you've been on the wait list for 4 years or 3.8 years, we're gonna say those are roughly equivalent. Or maybe depending on how we choose morally relevant goods, we might say, hey, just being a human being is the right qualification, and so everyone is gonna be equally in the lottery pool. And those all work from the claims perspective. And the sources of our claims could be desert, that you deserve it, need, or merit. But notice these are a little bit different from utilities. So utilities, which is something that I think we're more comfortable talking about in the computer science context, are comparable, similar to claims. But claims can linger even after the decision is made. So if I take the greatest utility action, I'm done. I don't owe anything to the people who didn't get the outcome. But claims suggest that I do owe something to the people who had a claim but who didn't end up getting the thing. And so they're also different from rights because rights aren't something that we can weigh up, whereas claims are something that we can weigh up. So claims are essentially comparative. And interestingly, the claims framework also suggests that we should allocate undivisible goods with a lottery. So I think this idea of using randomization or a lottery to spread chances over these different groups that might otherwise excluded is the right way to go here. And so what should we do? We should do something like that. So how are we gonna do this? Well, when I first started working with my awesome collaborators, Aisha and Shomik, I thought, okay, let's just make a bunch of models. The models are different, and then we use those models to make different predictions. And it turns out there's a good way for us to talk about that and formalize it. We can say, hey, in fact, there are many models that have the same accuracy, but different token predictions. Great, exciting. And we can even produce them on purpose. So we can use the phenomenon of model multiplicity to intervene at many different places in the modeling pipeline, make different choices, and create different models. And this set of models is sometimes called the Rashomon set. So Rashomon is a wonderful movie in which the same event is viewed by different people who participated in it, and they each tell materially conflicting stories that all fit the final facts. So the same guy was killed, the same murder weapon was found in the same place, but different people did it. So in a similar way, we could generate a set of equally well-performing models that have different token features. And we can arrange this in sort of like philosopher logical possibility style, where we can say the original model, that's going to be our at, that's going to be our home model. We can have a same accuracy model class. We can have an equivalent accuracy model class, so close enough. And then we can think about all the possible models, regardless of their accuracy. But what happens if we do that? Well, we create the multiply equally accurate models. We choose randomly among the models. We have this possibility of being classified otherwise. Looks good so far. We can have one model that gets 9 out of the 10 qualified candidates, but unfortunately rejects Amara. And then we have a second model that, again, same accuracy, 9 out of the 10, but unfortunately rejects Josephine. However, it turns out that what we imagine this Rashomon set of models might be doing is not everything that we hoped that it would. So if we think about the Rashomon set of models, no matter how fancy we get with our tricks, we're only going to recover a small proportion of the models that, you know, God or some better model generating entity could have made. So that's our dotted line within the possible Rashomon set. And we might hope that we are then getting equal accuracy allocations when we end up running the model forward and doing our predictions. But it turns out we don't. It turns out, unfortunately, the allocations we get, not only some of them are worse than others, some of them are not in an equal utility allocation set, but also they sample pretty unevenly from the set of possible equal utility allocations. And so it might be that we don't get this even spread over outcomes that we wanted. We can get 2 equal utility allocations where 4 out of the 5 qualified people are selected. But it might be that there are yet more equal utility allocations that we just never find. And we aren't going to find with the Rashomon set that we can create with the data that we actually have. So when we tried to do this, we indeed noted this. So if you look here at the cumulative proportions of qualified, so everyone on this graph is qualified, and so you might say, okay, how likely is that they're selected? Well, there are some people in this yellow circle who, even in our different ways of creating the Rashomon set, never get selected, and that's very unfortunate. And one way of thinking about this is that there are some qualified individuals who are consistently viewed as riskier than others, even within this Rashomon set. And so our conclusion here is that multiple models created from the same data can fail to evenly sample the space of equally good outcomes. And so from an ethical perspective, we have to stop here and say, okay, this prompts a question. What were the good applicants owed? Did we owe them that they actually got the thing? Did we owe them that they got it a certain percentage of the time? Let's say they applied to 100 jobs. What percentage do they actually need to move on to the interview stage? Do we owe them a chance at the good? If so, is it a proportional chance, proportional to their goodness, or just a non-zero chance? And when do we owe them that chance? So there's an interesting discussion in a paper called Good Reasons for Losers. I hope to make such a great paper title someday, where he argues something I think very extreme, which is if you're giving someone a chance, it's a chance that you owe them at the time of decision. So we would have to pseudo-randomly, or perhaps truly randomly in some way, choose between our different allocations at the time that we're actually deciding. It couldn't be the case that we have already done this random allocation, because then they never really had a chance. Okay, but I think the critique of the multiple model perspective suggests that we're not going to get the even distribution of chances that we wanted out of the Rashomon set anyway. So instead, what if we just do a lottery? So we have these likelihoods that we think people are an appropriate fit for the good, what if we just randomize based on those likelihoods? So if you are 79% likely to be good, we give you 79 lottery tickets in our lottery to get the actual outcome. I'm fine with this, but this makes a lot of people queasy because it means there are some cases where we give the 1% candidate the thing, and there are some cases where we don't give the 99% candidate the thing. So depending on your tolerance for exploration as opposed to exploitation, we could also think about having a quality threshold. So we could say, hey, we're going to cut off the extremes. We're always going to give it to the 99% person. We're never going to give it to the 1% person. But there's a big band about the middle that we should admit we're not that certain about. And that's where we're going to run the lottery. Now, this is a little bit weird because from a normative perspective, we're saying that we do have beliefs about the likelihood of these candidates, and we're just kind of arbitrarily thresholding them. So this is what's called a mixed strategy, which philosophers have some opinions about. But I think it is a lot more palatable in a lot of actual decision-making contexts. And as you can see, when compared with the dotted line, so just always giving the stuff to the people, and the straight line running a pure lottery, it's going to be in the middle. It is going to reduce outcome homogenization, but not as much. And finally, we could do something that does respect our evidence, and we could use conformal prediction or variance. So we could say, hey, we could set up the model so that we know which points the model is most uncertain about, and flip a coin to randomize those points. And it turns out many of those points are around the decision threshold anyway. And then maybe we don't have to lose a lot of accuracy depending on how many points we do this for, but we can drop outcome homogenization faster than we lose accuracy. So in summary, shared data, algorithms, and foundation models can all create or contribute to algorithmic monoculture. This monoculture can homogenize outcomes, and we should consider this to be a problem when it concentrates an unreasonable burden of errors or consistent rejections on individuals compared to other possible models. And to address it, each actor in the ecosystem should randomize their predictions. And with that, we hope that we can go from the algorithmic monoculture to a beautiful field of wildflowers. Thank you.